So in an earlier lesson, we learned about how we could compute paths using depth first search. I want to show you a broader, arguably simpler or reusable way you could compute paths from a given start vertex to any other vertex that is a part of the graph should it exist. So earlier on in the lessons, we talked about how when we run DFS or BFS, we end up with a spanning forest, and specifically if the graph is connected, we end up with a spanning tree. This is something that we've proven together. So you might ask, Dan, how can I use this information to compute a path? So when you execute BFS, for example, as we've seen previously, you can associate a parent attribute with each one of, parent or predecessor attribute with each one of your vertices. You can have a parent attribute for each one of them. So I can have a parent for each one of these. Namely, the root of the BFS tree or DFS tree will have it, that's the only one, because it is a root, will have no parent. However, each successive one will have whatever node it took to reach that one at its first occurrence would be its parent. So in this case, the parent of 1 is 2 because this is where we'd started off originally our tree traversal. Sorry, not our graph traversal. Sorry, I get very ahead of myself. So naturally, the parent of 4 would be 1, the parent of 3 would be 4, and the parent of 5 would be 3. Just follow along the discovery edges, because remember, the discovery edges form our spanning forest. So in this case, it's just a spanning tree. Now, do you see how I can use the information I have available to me to compute a pathway given two vertices? So for example, if I start off at vertex 3, notice that I have the parent for which they'll take me from 3 to 4, and this will take me from 4 to 1. This will take me from 1 to 2, because its parent is 2. I could trace myself all the way back to 2, say if I wanted to find the path from 2 to 3. So if I know a given vertex that I'm going to go frequently computing paths from it, say a given source, what we would call in the pathfinding terminology, the starting vertex or source vertex, say we have several times we would like to recompute that information. If we compute the DFS tree or BFS tree, we can keep these parent attributes around. If we have access to that given vertex, then I can trace through the parents to get back to the other endpoint of the path, or the other end of the path, to be a bit more precise. So let's talk about this. So previously I showed you how you can compute a pathway in a graph using DFS. We used a stack that we would hang around with, say that was accessible to our algorithm, or think of it as a global variable if that makes it easier. And we would store in the pathway, we'd use a stack to store that information so that if we pop off the stack, we get the pathway in reverse. Now, what we can do once we have this tree and we have access to both of the ends of the path, the desired one, if should it exist, we can say hang on to that information in a very similar way, except we don't need a stack to do it. We could just simply use a list because we have all the information to get from point A to point B. We don't need to have any other mechanism to help us along with this process. We've already computed that information. So suppose there is a list, which I'm going to call P, mean path. To store the path. And we're going to try finding pathways using the DFS tree or a BFS tree. You're going to see it's actually much simpler once you have this tree at your disposal. Like much simpler. And it's very easy to augment with different data structures should you would like to use, instead of a list, say something else. So one thing I also want to point out to you is, say for example, let's take our previous example. Suppose that I was using a list to store the vertices of each one of the ones in the path. Suppose I'm trying to find a path from 2 to 3. So suppose I want to get a 2-3 path. Or if you think of this as U and this is V, I want a UV path, which we've defined previously before. The idea we have two endpoints, the two ends of the path. So in this case, what I could do is I could store in my list. I can just imagine I have my list here. So I start off with an empty list. And you imagine at the end of this process, I would like P to be empty if there does not exist a path. But if it does exist, I would like it to store the vertices, or if I wanted to augment this, say if I have the list of edges, I could do that too if I would like that. I can have another list that does that. What I could do is I start off at V, so I just put 3 in there, and then I would follow my parent. And look, there's 1 for the parent of 4, but notice that I'm at 4, but 4 isn't like the furthest up in my tree, right? I haven't yet got the root yet. So I could just insert this at the front of my list, and then I can follow my parent. I go to 1, I can insert that at the front of the list, and then I could follow my parent. It takes me 2. I put 2 at the front of my list, and notice my parent is null. Notice that I have no other elements to consider at this stage. But notice now that I have, in fact, a 2-3 path. Notice that it's UV path 2, 1, 4, 3, 2, 1, 4, 3. The thing is, so I always insert at the front of the list. I can ensure that they're actually in the order from U to V in terms of the pathway. This is in contrast to the stack, which would give it to you in reverse. But it will be correct. It'll just be in reverse. So you'd have to just fix it by just popping them out and then just put them into a list in a manner that's quite similar to this. So now let's see how this would work. Now you might ask, Dan, what exactly do you do here? Now, because I didn't show you this specifically for BFS, like the BFS tree, I'm going to show that to you, seeing as I used in my example the DFS tree. So let me show you what the algorithm would look like if I was doing this with the BFS tree, but I must stress that it doesn't matter if it's the BFS tree or a DFS tree. I just wanted to pick one of them for you because in our notes, I have it where it shows you the explicit lines in pseudocode for building this tree. So we're going to call the algorithm. So algorithm is going to be called find BFS path. BFS path, breadth first search. We're not doing anything with binary search trees today. So it's input. We have the vertices U, V, which are in the set of vertices of some graph G is equal to V. Now, the big assumption here is that the BFS tree already exists. That's a very important element of this whole thing. It's that whatever tree that you're going to use, the DFS tree or the BFS tree, it has to exist already for this to work. So that's an important assumption. So this is an assumption that I'm going to make. So this would be a pre-computation. Assumption. We have the BFS tree. So we already have this. Welcome on in. Welcome on in. So now we have our vertices. And what we're going to do is we're going to have it so it returns true if the UV path exists and false if it doesn't. And I'm going to stress that this list P is going to store the pathway in terms of vertices. So true if we have a UV path that exists and is false otherwise. So watch this. This is going to be much simpler as an algorithm at least. because we already have all the information constructed for our tree. Now, I must stress that this is not a BFS tree over here. That's a DFS tree. However, the same principle applies. So this algorithm I'm going to present to you, it doesn't matter if it's a DFS tree or a BFS tree. It's just that, like I said previously, the notes already show you how to build the BFS tree. So I'm just sticking with that. So all we're going to do is we're going to have a reference to the one end of the path, namely V, and we're going to trace back over to U by following the parents. So wow. And when did we stop doing this, right? We stopped doing it when we hit null, right? That's when the parent was null. So we're just going to traverse along. We're going to go around on that pathway. But remember, the principle still applies, no different, whichever tree it is. As long as it's set up like this, where we have parent attributes or predecessors. So while this is the case, what we're going to do is we're going to insert at the front of our list. We're going to insert our current vertex. So this will place it at the front of the list, akin to our example. And then all we're going to do is we're going to update curNode to be the parent of curNode. So it's going to just feel like you're just doing a very simple traversal, okay? It's a piece of cake. You're just going to work your way back around like this. But the thing is, we're just going to always place it at the front of the list. That's why it keeps it in the correct order. If we put it at the rear, it's going to end up backwards, like on our example we did previously, where we used the stack. We were just doing cold turkey searching for a path. Now, once I have this information in my pathway, how do we determine if we found the UV path? How do we know if we found it or not? That's the big kicker. Well, surely U has to be somewhere in this list, right? But it's not just anywhere in the list. We could be much smarter than just that. Well, certainly, is U going to be at the back of this thing? Somewhere in the middle or at the front? Well, it's always going to be at the front of the list. Because every time we insert, we always do it at the front of the list. So it means all I have to do is just look at my list, look at list P, see if U is the very first element in P. That's all I have to do. And you can do that in constant time. If U is at the front of P, then, if that's the case, then you're just going to return true. Because that means you have a UV path. And in particular, P will store that information. So that means that if you go accessing P, it will have the path. Otherwise, we have to do some cleanup. Because remember, it may be the case that we start off V somewhere and then it just dies somewhere. It just keeps following its parents and then it just gets killed somewhere along the lines. It just couldn't reach U because U was not at the front of P. So it means that we need to clear out that list. So I must stress that this is only if you want to make sure, like keep in mind, if you're using this, if this returned true, that's how you know there's a path. If it isn't, then you could just clear out P and not use it, right? However, I'm just going to put just as a safeguard here, because if we're trying to be considerate to those that aren't going to do this, I'm going to empty list P. So that means that no path exists, no UV path exists. So you empty the list, so it means that you're going to potentially have to get rid of a whole bunch of vertices from this. So you're going to have to go through each one of these, get rid of those. So just remove them. And then you just return false, meaning that we failed to find the pathway. Now you might say, Dan, why would you show this only, because your example uses a DFS tree, why mention it in terms of BFS? Well, one, like I said, I already showed you how to do this with DFS, but likewise, I want to show you specifically with the BFS tree because as a reminder of something I've said in a previous lesson, this will actually, if you were to compute the BFS tree, which is, it won't look like this, what will happen is you'll end up with a shortest path tree. So it means that if you start off with some vertex u, like say you have this one here, and suppose that you did compute the BFS tree of this, you can keep reusing that BFS tree to compute shortest pathways from a given vertex to your starting one, your source vertex. So you keep using it over and over and over again. So this means that you can, if you have a BFS tree, you end up with paths that have a least number of edges between those two endpoints or ends of the path. Furthermore, it also lets you reuse it. So the one benefit of doing it where you compute the tree as opposed to doing it from scratch every single time is that if you're going to be recomputing pathways from U to some other vertex, you could keep reusing this tree over and over again. It'll save you time. So pretty fascinating stuff, right?